So yeah, I'm really excited to talk to you about materialized views. It's kind of what I eat and breathe at Dremio. So you might be interested in this talk if you are using Iceberg and you're thinking about accelerating your queries potentially with materialized views. Or maybe if you're a query engine, all right, you work on a query engine and you're thinking maybe I can produce, refresh and consume shared materialized views with other query engines. So, all right, so in terms of agenda, I'm going to first talk a bit about the benefits of having a materialized view specification in an Iceberg, right? And it really comes down to being able to have multi-engine interoperability with these MVs, right? Then we'll go into some basics around MVs, right? Like, what is it? Why do you want to have them? And then, I'll talk a bit about like how a query planner puts a materialization into a query plan, right? Then we'll talk about data freshness, right? So by design, a materialization is a cache, right? So it can get old, it can get stale, right? So you need to be able to validate the staleness and actually determine if it's still usable or not. And finally, we'll just get into the nuts and bolts of the proposed Iceberg spec changes, and we'll talk a bit about that. And so I don't have a whole ton of slides, so feel free to interrupt me and ask questions or raise your hand, right? So we can make this more interactive. All right. So why do we want to have a MV specification? So as I said, the primary goal really is to enable multiple query engines to produce, refresh, and consume shared materialized views, right? So like the probably most common use case out there would be if you have a query engine who's very good at doing data pipelines, batch ETL like Spark, right? Produce a materialization for a materialized view, right? And as part of creating this materialization, it would also write out like the query tree state so that so some other engine can know like what is the actual data and metadata inside this materialization. Then you have a downstream engine like maybe Dremio or Trino, who's good at analytical queries, right? And so when this analytical engine connects to the Iceberg catalog, queries the view, it sees that, hey, there's a materialization associated to this view, right? So why don't I just swap that materialization into the query plan, and now I can accelerate that query with this materialization that Spark built, right? So that is really the primary use case for having this MV specification to achieve this goal, right? Now, there's other benefits as well. So for example, like suppose you have like a tool like Tableau, right, or Power BI, and so they can connect an Iceberg catalog and they can see that there's a view, but they can treat this view as purely just a table, right? So they don't have the ability to parse the SQL inside the view, but they can see, hey, there's a materialization associated to this view, and it's also up to date, right? So I can go ahead and query that as just like a table, and you can just build your visualizations on top of that, right? So that's the second possible use case, right? An engine without needing to parse the SQL of the MV. And finally, if this specification is within Iceberg, right, then this can enable Iceberg catalog optimizations to validate the freshness. So you can imagine that when a client connects to the catalog and retrieves a view, right, the catalog will do in the background will process and check the validity of this view and say, hey, this view is actually up to date, right? Otherwise, if the catalog didn't do this work, then you can imagine that the client would have to make all these calls back to the catalog to check possibly 100 tables and views to see if they're actually what is the current version, what is current snapshot IDs, and does that match with the refresh state, right? So now you can enable these catalog side optimizations to do this bulk check, right? Does that make sense? Any questions or comments? All right. All right, so let's talk a bit about just the basics around materialized views, right? So a materialized view, you're basically pre-computing a view and taking a snapshot of its data, right? And when you take a snapshot of data, you also have to capture essentially the query tree at the time of materialization, right? And so we're talking about like what are the snapshot IDs of the tables that were used, like what are the versions of the views, right? So any sort of metadata change, you have to actually capture as part of that materialization. And so obviously the goal is that you're going to take the hit to write this thing once, right? And then downstream, you're going to be able to read this many times to accelerate many queries on top of it, right? Now, what are the specific acceleration benefits, right? So the most obvious one is that you're going to reduce the data size for the consumer, right? So if you've got like a engine that's querying this MV, instead of having to hit 100 billion fact record table, it's already pre-aggregated for him to 100K like summary table, right? So obviously that's going to be much faster. Another use case would be like reducing CPU, IO, and memory costs of like a distributed join, right? So very often you have data sitting on S3, you have data sitting on HDFS. You know, it doesn't matter if this data is an Iceberg table format or it's just a bunch of Parquet files, right? But to do this federated join, it's like very expensive to like, you know, send that data across the network, build those hash tables in memory, and then do this, and then, you know, do the join. So, you know, obviously if you take it out of query time, it's gonna be much faster with the materialization. And then, you know, another, you know, very common benefit is you get to optimize the physical data access, right? So like, you know, if your source data behind the MV is in CSV or JSON format, that's actually pretty slow to access, right? But when you create a materialization out of it, then you have a choice of, okay, I'm gonna write that into Parquet format. And not only is it gonna be in Parquet columnarized format, but I'll also partition and sort it to maximize my data file pruning or row group pruning, you know, based on the query access patterns, right? So you create this materialization specifically to accelerate, you know, your analytical queries. All right, so let's go into some more detail about how does a query planner use MV, right? So the most common, the most straightforward example is when, you know, a user issues a SQL statement and they directly query from the MV, right? And then at that time, the planner can say, oh, hey, this is an MV. It's got a materialization associated to it. It's also up to date. So why don't I just put it in there and, you know, now you just swap it and the query runs much faster, right? So that's, you know, that's a very easy thing to do. Easy thing for a planner to do, right? Now, a little bit more sophisticated planner will try to rewrite the user's queries, right? And so to give you an example, on your left side, there's this, here's a query where you're joining two tables, right? And then you're aggregating on top, right? Pretty simple. What the planner can do is that it can see that this aggregate can actually be decomposed and split below the join. And so what it'll do is it will rewrite that query to the right side. Right now, you've got aggregates on top of each of those scans, right? So then what happens is if you have a materialized view, for example, on top of the sales table that doesn't aggregate, which is, you know, grouping by the same, you know, columns as your original user query, but also the join key, you could potentially put that materialization into that, you know, onto that side of the join, right? And so here, the planner was able to rewrite the query to find a way to match materialization in, right? And so this is just one alternative that the planner can consider as a plan for that particular user query. All right, so kind of the way I like to think of MVs is that it's a relational cache, right? And the planner is really trying to fit the MV's query tree into the user's query tree, you know? And so when I say fitting, what I mean is that like the planner is trying to figure out what relational operators do I need to put on top of this materialization so that I can make it look like some part of the user's query tree. So for example, if your materialization projects more columns than what your user query really needs, right? You just put a logical project on top, right? And just select columns that you want and put that into the, you know, some subtree of the user query. If your materialization has more data than what the user query wants, you just add a filter on top, right? And then if your materialization aggregates is at a finer granularity, lower granularity than what the user query wants, you just add an, you know, aggregate operation on top. And now you can put that thing into the query tree. So at the end of, you know, this whole like logical planning pipeline, right? The planner is going to be able to see many different query tree alternatives. And so you need to cost which one is actually, which one will be the best cost, what will be the lowest cost. And so the planner has to explore many different alternatives, right? And just to give you a very simple example, you know, sometimes using materialization is not a good idea, right? So for example, if after you push all your filters down into your scans and that filter, you know, exactly matches how the way the table is partitioned, you may actually get, you know, access a lot fewer files by scanning the base table with filters pushed down versus going to the materialized view, right? So the planner has to be able to see these and make that determination. Now, typically, when for the queries that we look at Dremio, right, they're very complicated. They have maybe hundreds of views and hundreds of tables inside there, right? And so there's going to be MVs that match in many parts of the query subtree, right? And we have to figure out which one is the right one to use in the final query plan, right? Another thing I can point out is that even the same MV could have multiple materializations, right? So for example, you might materialize with different partitioning and sorting strategies, right? And like, for example, within Dremio, right, our MVs, we can materialize like a subset of the columns, or we might aggregate on some of the columns. So materialization doesn't have to be like, one-to-one with the materialized view schema. All right, so this is where it gets a lot more interesting. This is where in the Iceberg spec, there's been a lot of discussion, right? Which is how do we handle determining freshness, okay? So, the idea is that you're gonna have one engine that is producing the materialization, who's creating the materialization, but also writing out whatever state information that a consuming engine can then use to validate the freshness of the materialization, right? So I kind of want to illustrate this with a simple example, right? So suppose you have a materialized view whose SQL statement was select A1 sum B1 from A, join B, group by 1, right? So the planner is going to get the SQL statement. It's going to have to go and turn it into a query tree, right? And expand things out, right? And so you might have a tree that lists something like on the left here. And so what you'll first notice is that table A is actually a reference to a branch named ETL, right? And so the planner has to resolve that particular ref to the latest snapshot on that branch. And so that is the snapshot associated to the table A at the time of materialization. Okay, so that has to be reported, right? And then if you see the B identifier, it turns out, well, that's a view, right? So the planner has to go and expand that view out. And that view could be very complicated. It could be nested views and nested views and nested views, right? So in this case, B is just referring to table B. So table B, you also have to report its particular snapshot, on default main branch, for example. All right, and so all this is the query tree, and this is what needs to be represented in the refresh state. Okay. Now, in terms of Iceberg terms, what is the actual metadata that you got to capture, right? So first of all, you're going to have to capture the whole query trees, that MV's version ID. So there's a view version ID associated to this MV. So that's one piece you have to capture. The second is these table snapshot IDs, right? So that captures data state. And then finally, you also need to capture view B's version ID, right? So, that would completely capture basically the data state and the metadata state of that materialization. So for example, if the snapshot ID changed in table B, you would know that it's different. The consumer would see that it's different from what was last stored in the refresh state, right? And like for view B, that's not view B, like it's not a data that changes, but like metadata that changes. So for example, if somebody changed a filter condition inside view B, right? And that's obviously out of sync with the materialization. And so now the query engine has to decide whether to use that or not. All right, so let's get into the details of the specific table and view spec changes that are being proposed. First of all, a materialized view is no different from an existing view, actually, right? There's, the only thing that's different is now there's going to be additional property which identifies that this view has a materialization associated to it, right? So there might be like a table identifier or maybe UID, but it references out to a different Iceberg table, which we call the materialization storage table. So that's the first property. Is there materialization available? The second one is, what is the grace period of this materialization? So, it's very common across like different engines, right? That they have this concept of a grace period, which means that like how after this materialization is created, how long can I still keep using this materialization, right? Like what is that time period that I can still use that materialization? Now, what's interesting though is that grace period, the time that it starts, kind of depends on like what are the sources inside this materialization, right? So for example, if this materialized view is based on strictly Iceberg tables, right? Then you know when data has changed, right? Because snapshot ID has changed, right? So the grace period could be based on like, when you first detected a data change, and from then on, that's when the clock starts, right? But if you have a materialized view that is like, joining data from Oracle, for example, right? Then it might be hard to know when data has changed in that particular Oracle table, right? And so then your grace period might start from when your refresh of the materialization started, right? So that's something to think about. Now, as far as the table spec, so the materialization storage table is also just like any regular Iceberg table, right? And so the benefit of that is that you benefit from all the existing work and plumbing and functions that are available for table maintenance, right? Expiration and vacuuming, all that is you're going to need to do that, especially for incremental materializations. All right, so first of all is you need to have a property to track in the table snapshot summary, when was the materialization produced, right? That's just a timestamp, right? Now, the second one is where it gets a lot more interesting, and this is where a lot of debate has been happening in the community, right? And so if you follow the dev list, there's just multiple docs created on this, and there's just back and forth, but so there's kind of two options on the table. So what we're trying to do is try to represent the query tree state at the time of materialization, and we call that the refresh state. So how do we represent that, right? So the first option was to basically store that all within the materialization storage table snapshot summary, right? So basically it's like this big hash table, like this big table for each table, for each version, what is the snapshot ID, what was the view version ID at the time of materialization, right? So that was one design, right? Another option was, okay, why don't we capture the view lineage, right, in the view? So for example, if you've got a materialized view, you would also include in the view's lineage, what are the child identifiers inside this view? Like what views does this view use? What tables does this view use, right? And it would just be, listed out. And that's the lineage of that view, right? And there's obviously a lot of benefits of having this besides just for materialized view specification, right? And so once you have this lineage in the views, then the materialization table can then reference that lineage and then associate that lineage to the actual snapshot IDs and view version IDs. So this is one area where it's still being discussed, right? Another interesting thing that we're still discussing is like, well, how do you reference a table? Like, do you reference a table by its UUID, or do you reference it by its SQL identifier, right? Now we know UUID is definitely unique, right? But the SQL identifier for a table, right? If you ask like two different engines connected to the same catalog, what is the SQL identifier of this table? They may not give the same answer, right? And why is that? Everyone answer? You're nodding your head. Why is that? So if you have table, right, a given table that like Spark is referencing, the fully qualified name that Spark uses could be different from the fully qualified name that Dremio uses, because the first part of this name is the catalog, right? And that catalog is an alias that the engine uses for that particular Iceberg catalog. So these identifiers, if they're fully qualified, are not like engine agnostic. Okay, so this is my last slide. So I think one really important design consideration for this specification is how do we come up with a way that the consumer can quickly validate the materialization freshness, right? So so one idea obviously that's easy to do is to use the refresh start time as an approximation of the refresh state, right? So obviously, if the materialization was built 1 hour ago, then your data can't be more scaled in an hour, right? And that by itself could be sufficient for an SLA on a dashboard, okay? And so in that case, you wouldn't even have to do any sort of query tree checks or metadata calls, to validate that materialization. Now, if you have to check, you have to ensure that the materialization is not stale, right? Then you actually will have to go and expand the query tree and diff with the refresh state. And in that case, then you want to have a way to be able to parallelize these metadata calls to the Iceberg catalog, right? So that's gonna, and so that has to be possible, right? So your planner might, may need to build those capabilities. And then finally, ideally, you minimize the client server calls between the query engine and the Iceberg catalog. And so this goes back to my first point that I'm saying was that we can build optimizations into Iceberg catalog that can do that validity check for you, right? Because if the Iceberg catalog is the source of truth, was brokering all the commits to the catalog, then it knows what is the latest snapshot, what is the latest version of every view. It doesn't have to go out to storage to look at metadata JSON. They may have already cached that, in memory inside the catalog. And so for it to do, 100 checks, it would be trivial. But if the engine had to do it, it would be very expensive. All right, so thank you. I have listed out a few resources. There's many Google Docs that are floating around regarding this spec, but this is the one that's the main one that so you can click on that to read about it. If you want to learn more about materialized views, how, why, what, and when is it right to use it, I think Dremio has really good best practices documentation that you can just take a look at to see how do you accelerate queries with a materialized view. So yeah, with that, thank you for joining my presentation.
Let's see, yeah, we got time for.
I had a question. Go back about 3 slides. I was curious if DVC and Dremio are competitors or collaborators, or as far as materialization of views, is that kind of an industry standard? Because they also kind of use that.
What was DVC?
Yeah, DVC. It's like data version control we use in machine learning.
Okay, I don't know what DVC is.
Okay.
But I mean, what we're trying to achieve is inter-engine interoperability with materialized views. So one engine is good at ETL, let them create the materialized view. Another engine is focused on accelerating queries, then they should use the materialization. Yeah.
Apologies if I missed this. Who provides the compute to refresh the materialization?
It would be whoever's producing the materialized view.
It's only the producer, it's not the consumer at any point.
The consumer could be a producer as well, right? But I mean, like for example, Dremio builds can refresh materialized views, do them incrementally as well, and also use them in queries, right? But if your pipeline is set up so that like Spark is going to do most of the ETL, right? Then you may have Spark do that once it's updated space tables. Yeah, Kevin.
Because you're on this slide, is there a difference between? Because you said something about table materialization. Is that the same as materialized view, or are there two different concepts?
Yeah, it's two different concepts, right? So materialized view is just the view, right?
So you have tables and views, and you have materialized views and materialized tables?
No. So view and materialized view is the same thing, except that view has additional property that say, hey, I got a materialization. Or like I have a cache, I have a copy of it, right? And then materialization really refers to that storage table. Okay, that has the cache copy or snapshot of that view at a particular point in time.
Yeah. So it's the underlying storage, not the view.
Yeah, it's not the view definition.
Sure. Is Dremio one of the main drivers of this spec in the Iceberg community?
I think there's a lot of people involved. I wouldn't say Dremio is the main driver.
Who would you say is like the main drivers of this?
I'll say like Jan Call. I probably pronounced his name wrong. He's the main driver. I think he has his own company. And then Walla from LinkedIn. We have a lot of discussions. Daniel Weeks, he was also quite involved with this. I mean, I'm sure I'm leaving out other people. Steven has also commented as well many times. So there's a lot of people interested in this right now.
Well,
Yeah.
In your past query, right, like, where you were showing the materialized, can you just go back to that query? Yeah, this one.
Yeah.
So how do you know, like, all these three are exhaustive to know that your refresh state is correct? Like, the version ID, snapshot ID, and view version ID. Like, how do you know that this is exhaustive to determine the refresh state of materialized?
Because okay, so the table snapshot IDs represents data, right? So if a data change occurs, the snapshot ID changes.
Yeah,
Right?
so only one is enough, right? Like, why do you need like the materialized version ID and view version?
Yeah, so the view version ID references view, right? So for example, if let's say there's a filter operator over here, right? And that changes, right? And then you materialize it before it changed, and then somebody changed that filter operator, removed it, right? Then that view version ID will change. So now you have to capture that view version ID.
And about the MV version ID?
So the MV version ID is, imagine like a project change up here, right? Because this whole thing is captured by the MV, right? Yeah.
Do you support changing field definition? And if the field definition is changed, how do you deal with the existing materialized?
Okay, so that's a good question, right? So that depends on the query engine, right? So, the query engine, in order to meet its SLAs, right? It may say that like I can tolerate any sort of data or metadata change within a certain time interval, right? So like for example, if you build a materialization to ensure that your dashboard query runs sub-second, right? Just because the view changes doesn't mean that you want to immediately invalidate that materialization, right? So that so the answer to your question depends on what the engine wants to do. Some engines, right, don't tolerate any staleness, right? So if an engine sees that this materialization is stale, I cannot use it to accelerate a query, especially transparently.
Would you want to keep refreshing your materialization, like as soon as the underlying table changes in data, or would that be super computation expensive to keep updating it and keep it completely fresh?
Yeah, so that's going to really depend on use case, right? Because that's going to be expensive, right? If you have a table that's constantly changing, right, and you're constantly trying to keep up, with updating the materialization, that will be very expensive.
Do you recommend like a 15-minute or 5-minute or how long kind of time refresh every hour, or
I think it depends. All right. So I mean, to get into further details, right? Then you have to look at incremental refresh, right? Whether you can incrementally refresh the reflection or materialization. But I think in general, if you're constantly rebuilding that materialization, that's going to be way too expensive.
I think we can also add some smartness to it. So the materialized view is nothing new here, right? So database industries, they have built this materialized view 2 decades ago. What we are really trying to do is reinvent all the wheel the database industry has done, right? And so another similar concept that some other compute engine built is intermediate query result cache. So they are almost identical with materialized view. So to answer the question, it would be inefficient and super wasteful to recompute the materialized view every time a table changes, right? It really depends on, because let's take a time series use case table, right? Because you partition the data and you're only looking at the first 3 months, first quarter of the data might not have changed in that particular quarter that you are interested in. The data might have changed some other quarter, some other year, some other period of the data, right? So you can add in smartness to say the materialized view has its own query construct and its predicates and what data it is trying to consume. And you can basically make a decision to say, is that change, am I interested, or did that change impact my query result? If it didn't impact your materialized view query results, you don't need to recompute it, right? So I don't think those kind of optimizations are built in, but these are some of the optimizations and innovations that you can add into it. Like, as I said, intermediate query result caching. AWS Redshift supports it. The simple way they do is anytime you do a DML operation, they throw up their hands and say, I cannot use this intermediate resource caching anymore because they don't have the smartness and logic to detect when this intermediate query result caching is valid and invalid, right? They just go by simple logic. So I didn't mean to take too much time on that, but I thought I just want to add more context to it. There is more optimized ways to build it.